Hello and welcome back to Vegas October 1 Sounds. Been a couple days now. Tonight I want to talk about a multi-part series I'm doing on the various effects of sound, elevation, speed, walking, all this sort of stuff. And I'm going to do it in very graphic detail to make things understandable. And from this understanding, you'll be able to look at some of the graphs I do, and you'll also be able to analyze what other people do and come to your own conclusions about what's happening. So let's start right out. In this scenario, I propose that we have a source of sound located at point A, and 1,000 feet distant, I have a recorder at point B. And we're going to do this in a 2D planar view, that is, we're looking down on this situation, and I'm going to ignore all three-dimensional aspects of sound propagation. And this makes the analysis much easier, and we can extend it later to a three-dimensional situation. So in this scenario, we have the speed of sound at a comfortable 1,000 feet per second, which is a bit slower than that evening in Vegas, but 1,000 feet per second is a nice round number for calculations. As the distance between points A and B is 1,000 feet. And the sound source at point A, which is also has a recorder there, emits 4 pulses. And the first pulse, shown in this diagram here, is on the outside. And then the second pulse, third pulse, and fourth pulse. Each one of them is separated by 1/10 of a second. So it's nice even numbers, nice round calculations for the most part. So given the 4 pulses, there'll be 3 intervals total, each with a time of 1/10 of a second, for a grand total of 3/10 of a second. So between pulse 1 and pulse 4, 3/10 of a second. As you can see, in this case, we're modeling point A as a point source in a 2D plane. That is, the sound propagates outward from point A and equidistant in all directions. So it doesn't matter whether you're on the top or at the bottom, on the left or the right. The sound is propagating equally in all directions, and you'll hear it correspondingly. So the first wave is marked right there. If we tabulate when the waves arrive at point B and are recorded, we can see that for the sound traveling at 1,000 feet per second to cover 1,000 feet, it will take 1 second. The same wave here, when it was back there, back at point A, will cover the same 1 second plus the time it was emitted, which is 1/10 of a second later. So it'll record at point B at 1.1 second, and correspondingly each subsequent wave will add another 1/10 of a second for 1.2 seconds and 1.3 seconds. As I've done in many times, I've measured the delta between these, and it's 0.1 seconds, corresponding to exactly when these pulses were emitted. So this is a static situation. It's static in the sense that both A and B are fixed and are not moving, and we'll get to moving later on in this video. I'll also do other videos covering the effects of elevation and the multi sources, multi recorders, and alignment of these things, and I'll show you exactly how I work in my research. Alright, so if we were to take the audio from each of those recorders and plot it on a waveform, it might look something like this. This is the timeline for the recorder at point A. And here you can see that early on we get the first pulse recorded, the second pulse, the third pulse, and finally the fourth pulse. And since A is right on top of the recorder at A is right on top of the source, there's no time delay before them. So we got a nice little 3/10 of a second grouping here. And then if we look at what happens at the point B in the recording, we'll see that it has to travel for 1,000 feet or 1 second, which is indicated right here, and then the first pulse gets recorded at 1 second into the recording. And subsequently there will be 3 more pulses each with a 1/10 of a second delay from the first one. And here I've just added in the numbers to make it very, very clear what's happening. Alright, so we got this static situation with a point source emitting 4 pulses and 2 recorders. And this is how on the waveforms it will visualize. Alright, so now we can move on to what happens to these waveforms when the person or the recorder at point B is moving away from the source at point A. But first we have to talk about how fast we're going to be moving. So let's take the first example as a walking speed, which I estimate will be about a little over 3 miles an hour, and I've chosen 3.4 miles per hour because once again when you get down to the bottom line it's a nice easy number to work with. So if we're traveling along walking at a casual pace of 3.4 miles per hour and there's 5,280 feet in a mile, then we're going to cover a nice comfortable 17,952 feet per hour. That's quite a thing, but we're not going to travel an hour, of course. So how many feet per minute are we traveling? Well, so that's 17,952 feet per hour divided by 60 minutes per hour gives us 299.2 feet per minute. So every minute we're traveling around 300 feet. Okay, now let's further divide that down into how far we're traveling or how much we're traveling every second. So we take the 299 feet per minute and we divide it by 60 seconds per hour, and we come up with 4.989 feet per second. Well, that's close to and good enough for me if I just call it 5 feet per second. So the grand total here is that if we're walking at 3.4 miles per hour, we're traveling 5 feet, roughly speaking, not roughly, actually fairly close to 5 feet per second. So now we know how far we're going to move in a second. And I like seconds because sound, in this example we're using 1,000 feet per second for sound, which equates out to 1 foot every 1,000th of a second, or every 1 millisecond. Okay? Alright, so the scenario is this. Here we got the point source over here at A on the left, and 1,000 foot to the right is point B. That's the same exact scenario as up above. So if the point B, if a person at point B is recording the sounds made at point A and walks away from point A at this 5 feet per second, when will the 4 pulses be recorded? Well, there's many different ways of looking at this, but let's do it in a simple, direct, incremental way. So any pulse emitted here has to first travel this 1 second distance. And as we know, the person having 1 second to walk away from there is going to travel another 5 feet away. So at 1 second, we're going to be at 1,005 feet away from point A. So it took sound 1 second to cover that distance, and it's going to take it another 5 milliseconds to cover the distance that the person holding the recorder traveled in that second from B to B prime, and the person is still moving. So by the time the sound has covered that 5 feet, in this case the person will have moved 5 milliseconds times 5 feet per second, or 0.025 feet. And then we can add all that together. Well, that would go on ad infinitum until finally the 2 points collide. Now, so if we add up all that stuff, we have the 1,000 feet from point A to point B, plus the 5 feet traveled in that 1 second by the person, plus the 25 thousandths of a feet traveled by sound in the time it took it to cover 5 feet. and we divide it by the speed of sound, and you know, there's many more elements here, but all these things quickly go to 0, and essentially for our purposes we can eliminate it to the first two terms, which would be the 1,000 feet or 1 second and the 5 feet or 5 milliseconds. So if you wanted, we can take it to the third term. If we add all those up, we'll get 1.005025 seconds at the point where sound overtakes the recorder. Okay? So, that's for the first wave. What happens with the second wave? The second pulse. Well, for the second pulse, it has to travel both the distance of 1,000 feet, plus it was delayed by 1/10 of a second. So to reach point B, it's going to take 1.1 seconds. Okay, well, in that 1.1 seconds, person B traveling at 5 feet per second, you just multiply these two together, is going to have moved 5.5 feet. And since we're only taking the first two terms here, then we're going to get 1 second plus 5.5 feet over 1,000 feet per second, or bottom line 1.1055 seconds. And we can do that for the remaining two waves. And if we calculate it all out, we'll get the times of arrival. Okay? And they're listed right here. As you can see, the delta between them has changed. It used to be 0.1. And because the point B is moving away, the effective length has increased by half a millisecond, or yes, not very much. That's for each interval there. Over here, well, I'll just read it here to you. Viewed another way, the interval between successive waves has uniformly been increased by 1/2 of a millisecond. And thus the width of the event from the start of the first wave to the start of the fourth wave has been elongated by 3 intervals. Remember, there's only 3 intervals between them, each of them half a millisecond, for a grand total of 1.5 milliseconds in lengthened over the original. And thus the perceived frequency of the wave is lowered accordingly. Alright, I don't need to rewrite that, so let me just eliminate it right while I'm here. Alright, and if we plot this against the original times of arrival, there's very little difference between them, because after all, half of a millisecond is not much. The normal resolution that I use in measuring these sounds with Sonic Visualizer is on the order of 1 millisecond. So half a millisecond I'm not going to notice. And that's all I said here. Alright, so what happens if rather than just having four pulses, we have 100 pulses? Well, we can ask the very same questions, to go through the same calculation. So if we're traveling at 5 feet per second and we have a 100 pulse stream, each consisting of 0.1 seconds, we have 99 intervals between those, and we multiply 99 by 0.1, the duration of the whole thing is going to be 9.9 seconds. Okay? So we ask ourselves, how far a person walking or traveling at 5 feet per second will travel in 9.9 seconds, and we just multiply it out, and it comes out to 49.5 feet. And thus the arrival time of the last pulse will be 49.5 milliseconds after the equivalent time of a stationary pulse. So now we're talking, so here we go. If we have the last 4 pulses of a stationary 100 pulse long signal, then versus the same signal only recorded walking away, then this difference between the last pulses is going to be 45.95 milliseconds greater for the person walking. Alright, so essentially as you walk away, you're increasing the distance from the source, and it takes the sound longer to get there. You can look at this. There's an equivalent phenomena using the same type analysis, maybe a little bit different math, called Doppler effect. And the Doppler effect states that if you have a moving source relative to a sound, then as you move away, the frequency of the sound drops, i.e. the length between one crest of one pulse to the crest of another lengthens. Correspondingly, if you're moving towards the sound, the time between pulses shrinks, and consequently the frequency goes up. And we've all heard this, when you hear a train go by or a siren go by, as it approaches you, the sound gets higher, and then immediately after it passes you, it gets lower. And that's all due to this same effect that I've displayed here. All right. So, what about longer recordings? Here we've recorded 10 seconds. What if we have a minute-long recording and it's recording a person walking away? Well, as you can imagine, if we take a 30-second recording and a person is walking at 5 feet per second, then we're going to get 150 feet increase in the distance away from the source, and at the speed of sound, that's 150 milliseconds. And if the gap between these is only 100 milliseconds, then the shift is going to be more than one gap. And now you're starting to see a number which, since I'm measuring things at about 1 millisecond, is a pretty large number. So the takeaway here is that even for slow speeds of walking, if the recording is long, then the shift in the time between the pulses and the overall length increases to a measurable amount. If you have a short pulse, it's hard to discern it. Now this is all for walking speed. What if we jump to the speed of a slow car? So let's just multiply our walking speed by 10. Okay, so we'll go, instead of 3.4 miles per hour, we'll go to 34 miles per hour. Okay, well, we can use the same calculations as before. That's 10 times faster than walking. And we can ask, what will be the shift in the recording at point B? So instead of 5 feet per second, we're going at 50 feet per second. And we can calculate the time of arrival for the first pulse. Well, the pulse in going from the source at A to the recording at B, that is 1,000 feet, so it'll take 1,000 feet divided by 1,000, which is 1 second. And in that time of 1 second, we will have, traveling at 50 feet per second, okay, well then we'll get 50 feet. And so 50 feet divided by 1,000 gives us 50 milliseconds. And similarly, the next term will give us 2.5 feet over 1,000, which is 2.5 milliseconds. So using 3 terms, when we have 10 times the speed, we'll end up with 1.0525 seconds, or essentially 52.5 milliseconds longer than if there was no movement at all. Okay, that's quite measurable. All right, and the interval between each pulses is going to end up being, if you run through the numbers and everything, 0.1. Let me make sure I get this right now. Yeah, the gap's going to be the original 1/10 of a second plus the 52 milliseconds. That doesn't quite seem right to me. Oh yeah, here we are over here. The second 2 terms, because we're eliminating the first one. That is correct. So the incremental addition is the second and third term, which ends up being 52.5 milliseconds. So from pulse to pulse now, instead of having 0.1, we're going to have 0.1525, which, if we measure the whole 3 pulses, 3 intervals, is going to end up being 0.1575. Yeah. Let me do the math here now. 52 milliseconds times 3 is going to add, I don't believe that. Did I write that down wrong? If we have if we have, I think I did the math wrong here. If I have 1 second to travel, if I move in 50 feet per second times 1/10 of a second, then I'm going to move 5 feet, and that's going to be 5 milliseconds over and above that. So that would be I think I better go back and redo that calculation. Alright, let's see. Alrighty. So up here when we're at 3.4 miles an hour, the delta between them is half a millisecond. Therefore, at 10 times that speed, we're going to get 5 milliseconds added on. Okay, so it's going to be 5 milliseconds extra per pulse. Yep. Okay. That jives with this little calculator. So, we have 3 intervals, so that's going to be an additional 15. Yeah. So it's going to be 15 milliseconds longer, basically. Yeah, this statement here is a little bit wrong, and I need to rework it. So let me put it in there. And I'll come back and I'll correct that with an addendum, either my next video or the following one. All right. So that's an introduction to the effect of movement on the arrival time of sound. In general, we call that the Doppler shift, and as we move away from a source, it elongates the time. As we move towards the source, it shrinks it. All right. Grab you on the next one.